Welcome to this training provided by Efficiency Vermont on behalf of the Energy Code Assistance Center on prescriptive compliance with the 2020 Vermont Residential Building Energy Standard. The Vermont Residential Building Energy Standard, or RBES, was enacted by the Vermont legislature in 1997 and typically it has a 3-year code revision cycle. The last code that is in force at this time is the 2015 RBES. We today will be going over the updates and the current law of the 2020 RBES, which will become into effect as of September 1st, 2020. So any projects that begin after or on September 1st or are permitted on or after September 1st are required to meet the standards of the 2020 RBES. Any projects ongoing or begin before September 1st, 2020 are required to meet the 2015 RBES standard. The content of today's training covers the full detail of the 2020 Vermont RBES code, while there is also the 2020 Vermont RBES Handbook, which is a guide to the implementation and application of the code. It is important that we understand that there's a distinct difference between the full RBES code language itself and the RBES Handbook. The full RBES code contains all of the applicable code requirements for the application of the code and is what this training is based upon. The handbook or guidebook is a summary guide that highlights the key requirements and methods for compliance of the code and is meant as a way to summarize and provide content to implement the full rule of the code. The guidebook or handbook should not be used as a substitute or replacement of the full RBES code. The full 2020 Vermont RBES code publication is available through the International Code Council at the website located on this slide, as well as a link through the Vermont Department of Public Service, while the 2020 Vermont RBES Handbook is a publication created in partnership by the Vermont Department of Public Service and the Energy Code Assistance Center and is available through the Department of Public Service on their website. Questions regarding the content of the code and the application of the code can be directed to the Energy Code Assistance Center or the Vermont Department of Public Service at the contacts listed below. So the focus of today's content is on residential new construction and additions, but which buildings must comply. So new construction, low-rise residential, so this would be 1 and 2 family dwellings, multifamily housing, 3 stories or less. Anything larger than that would require to meet the commercial code. It does not include commercial buildings, but it does include the residential part of a mixed-use building. So if you have a building that has commercial retail space on the first floor and residential rental space above, the residential portion of that building must comply with the RBES code. Existing residential buildings has its own section. Again, today, what we will cover today will apply to additions. With an addition, only additions need to conform, not the existing house. Renovations and alterations have their own requirements as defined in the code. This is covered in Chapter 5, Existing Homes. We will have a separate training on Chapter 5, Existing Homes specifically. Also, all projects that require Act 250 permits are required to meet the provisions of the stretch code, which we'll cover today also. And stretch code is also required in certain jurisdictions in the state that have adopted it. There are certain building types that are exempt from meeting the full rule of the RBES code. These include low energy use buildings. So there are parameters set forth in the code that if a building only consumes a certain amount of energy in its use, those buildings are exempt. Unconditioned buildings, so we're talking about non-residential, unoccupied buildings. Mobile homes have their own separate requirements under federal guidelines for mobile home manufacturers. Hunting camps, seasonal use buildings, buildings that are not occupied in a year-round manner. Summer camps similarly, so this would again be a similar unconditioned building. So as it specifically applies to this, any buildings that do not have fully distributed heating equipment in them. Yurts has its own exception, and older owner-built homes. So there is an exemption for owner-built homes to not comply fully with the rule of the RBES Code under the strict conditions that are put forth in this section. All of these requirements must be met, including that the owner of the residential building is the builder. The residential construction is used as a dwelling by the owner. The owner directs the details of construction. The owner discloses in writing to a prospective buyer before entering into a purchase agreement the nature and extent of any non-compliance with the RBES. This does not mean that an owner-built home does not need to meet RBES or should not meet the full rule of RBES, but there is this provision put in place strictly under the definition of owner-built homes. Existing buildings. So this is Chapter 5 of the RBES Code. Again, we have a separate training which will cover this in full detail. So this is a summary of the buildings that will be required to meet the RBES rule under Chapter 5. So additions, alterations, repairs, and change of occupancy or use are all areas that will require RBES compliance. So if a building is having an unconditioned part of the base space become conditioned space, that triggers compliance with RBES. Insulation projects where insulation is being installed into an existing home must meet the requirements of the existing home section. Replacement windows also must meet the requirements of the existing home section. Some exemptions are unaltered portions of a building. If there is a remodeling or a retrofit going on of a building, areas that are not affected do not need to comply. Replacement of a glass or storm windows in an existing window do not need to comply. Any exterior envelope assembly, walls, ceilings, floors, if they are already filled with insulation during exposure or during a remodel, they do not need to be altered or changed. Similarly with re-roofing, unless a roof cavity is exposed during the re-roofing project and that cavity is not filled with insulation or empty, that area does not need to be improved. If the cavity is empty or not full, it is required to be at a minimum filled with insulation. The lighting requirements of the code do not apply unless you have more than 50% of lighting fixtures being replaced, as well as repair of existing fixtures. So one of the things that is unique about the Vermont RBES Code is that it is a self-reporting and self-compliance rule. There is no code enforcement from the state level as far as code inspection or code oversight. So a builder is required to comply with the law and submit documentation that he or she has. Liability to the builder can come from the homeowner who, under the rule of the RBES, may take civil action against the person who has certified the building as being compliant. So if there are portions of the building that are deemed to be non-compliant with the code, the homeowner can seek damages, including for the increased energy costs and costs to bring the building up to compliance of the standard that was effective at the time the building was built. This can also cover court and attorney's fees, legal fees to that liability. Claims must be filed within 6 years of completion of the project by the owner. And we are seeing that there is more and more attention being paid to the code, the awareness of the code, and the rule of the code by lenders, titles attorneys, and local town officials looking for RBES certificates and verification that buildings are meeting the full requirement of the code. So general requirements of the code, the next few slides are going to cover the chapters that exist in the full code as a summary, and then we are going to get into the details of prescriptive compliance with the 2020 RBES. So Chapter 1 of the code covers the scope and administration of the full RBES rule. So this basically covers the application, enforcement, administration of the requirements of the code. It also identifies which buildings and structures are under the guidelines of the RBES code. Chapter 2 is definitions of building materials, assemblies, systems, design conditions, equipment, etc., as they're referenced to and apply to the full rule of the code. This is an important chapter. I recommend everyone at least becoming familiar with the content of to understand some of the different items that are mentioned and discussed in the code for applicability. Chapter 3 covers the general requirements of the code within the context of the design conditions and details and parameters for residential construction. So the real intent of the RBES code as a tool is to be used as a guidance document for building design. So this chapter covers the design conditions for modeling the building design, materials, systems, and equipment that are required under the purview of the code, identification and default values for some of these materials and systems. An important element of this chapter is design criteria for whole house ventilation for new construction. Any new building is going to require a whole house mechanical ventilation system, and this chapter goes into detail about the requirements of how that should be specified and designed, and also covers the parameters of combustion safety for fuel-fired and other combustion equipment within the home. Chapter 4 is the main heart of the code, residential energy efficiency. So this chapter covers the full energy efficiency related requirements for the design and construction of residential buildings. So this has all of the detail that we're going to cover in this session as far as the individual component requirements and compliance methods. And finally, Chapter 5 covers the requirements for existing homes. And as I mentioned, a separate training has been created that will cover in detail the existing homes requirements. So there are 3 different compliance methods for meeting the intent of the code. The prescriptive method, which involves packages and tables including specific component requirements for a building to be built by. The software method, which is the ResCheck software tool, where a full building analysis is done as an alternative to the prescriptive approach. And then finally, the home energy or HERS rating score pathway for meeting compliance with the RBES rule. And this is a more customized whole building weighted value approach to being compliant with the RBES rule. What we are going to cover here in the balance of this training is the prescriptive path for compliance for new construction and additions. So sections R402 1.1 through R404.3. The reason we're focusing on the prescriptive compliance path is that this is the method that most builders and practitioners will follow to meet the full intent of the law. So the prescriptive package approach provides the advantage that it's a simple method. You pick a package that you're going to design and build to, and you meet the full component requirements of that package and follow the basic requirements of the rule, and you will be compliant with the RBES code. There are really not many calculations that need to be done. You're not looking at valuing one portion of the building versus another and weighted values. This is something that really just requires following the guidelines contained in either the code guidebook or the full code book itself. The only drawbacks to the prescriptive approach are that it is somewhat inflexible. You do need to meet specific requirements in the different code packages, so it may limit some certain types of construction or types of homes. There are some higher component values with the changes to the code for 2020 that may or may not be practical for some cavity fill only wall options. And you must comply with the full conditions of the RBES code. So there are no offsets available as there could be or would be through the ResCheck or HERS methods for compliance. So the simplicity of the prescriptive compliance method is here in this table. A builder can choose which package they would like to build to, and you need to meet the full component requirements of each of those packages. So you cannot mix and match from one package to another, but you can choose to meet package 1, the standard approach, and you'll be required to meet all those component values in that column listed there, or pick a different package, package 4, and meet all of the requirements in that column there, and be compliant with the code with the additional conditions that we will touch on here in the next coming slides. An important distinction here is that log homes have their own prescriptive package, which we will not cover directly in today's training, but has its own section in Chapter 4 in the RBES code to reference as far as log home requirements. So a big difference from the 2015 code to the 2020 code, along with some of the updates to the component requirements in the table listed on the previous slide, is that the prescriptive approach for 2020 requires that the full component requirements of a package be met, and then points be earned based on the square footage of the house being built. So you'd be required to pick a package from the previous table, and then based on the square footage of the house that you're building, need to attain the number of points that are listed in this table on this page to meet the prescriptive compliance. So the number of points needed is determined on the building size by the finished condition floor area of the building, including unfinished basements and storage spaces. So it's pretty much covering the full square footage of the building. Another distinction, multifamily dwelling unit size is based on the average dwelling size for the building. So there is a distinction between square footage under 2,000 feet in multifamily versus larger. So points are earned by referring to table R402 123 in Chapter 4. So this gives options for different building components for upgrades to the base code requirement that is in the package that you've chosen, and the set number of points that can be earned by upgrading certain areas of the building and components of the building to earn the number of points that you're required for based on the building size. So the points covered not only include building envelope components, but also mechanical options and equipment options for the building that can attain points. So as mentioned at the beginning of this training, stretch code is an alternative to the base code, which is required under certain circumstances, such as Act 250 permitted projects and within certain jurisdictions in the state of Vermont. Stretch code is a more stringent requirement of the RBES code that has its own separate prescriptive package and points requirement. So Section R407 of Chapter 4 covers the full requirements of the stretch code, but similarly to the base code, there is a prescriptive package table. Note there are only 3 packages available to meet stretch code, and some of the individual component requirements are greater than the requirements of the base code. The points requirement for stretch code is similar to base code, though more points are required per square footage than the base code. So points available for compliance with the stretch code can also be found in Chapter 4, Table R407-213, and those components and their point values are listed on this slide and the next slide. The stretch code points value continued. So as well as meeting the specific requirements that are outlined in Section R407 in regard to stretch code, all of the base code requirements shall be met as well to the guidance complied in R407. The compliance with stretch code can be earned through this package plus points approach that we've just covered here, or you can also comply with stretch code by the HERS rating method, which we will not go into detail on in this session, but the HERS pathway is another option to comply with the stretch code. The res check method is not an allowable compliance method for stretch code compliance. One of the other items that stands out within stretch code is that there are specifications and requirements around solar or PV implementation with residential new construction, and that is detailed in Section R407.5. So we've gotten through stretch code, so now we're going to switch back to the base code prescriptive requirements. So there are alternatives or an alternative to complying with RBES prescriptively without meeting the full component requirements that are listed in the prescriptive package table. So that means there are alternatives if you choose to or are unable to meet a component or components of a prescriptive package. That is the U-factor alternative, which can be found in Section R402.1.4. So this is an assembly alternative to the specific requirements of the components in Table R402, and we'll go into some more detail about the difference between a U-factor assembly versus R-value components. One item to note, though, through this alternative is that the building still must comply with the points that are required based on the building's square footage that were noted in the tables previously. So also within the U-factor alternative option, you can comply prescriptively without earning any points, as noted before, but the U-factor assembly values must be less than those specified in Table R402 to be permitted as an alternative to points required. It gets a little convoluted here, but it is another alternative that allows a little bit more flexibility, but it does require more stringent performance requirements to the building envelope. So building air tightness requirements will need to be 2 ACH 50 or less tested versus 3 ACH 50 as allowed under the prescriptive base code requirements. And also balanced ventilation, HRVs, ERVs are required to comply with this alternative method versus the option of exhaust only ventilation being allowed under the base code prescriptively. So table R402.1.4 are the equivalent U value or U factor components that are allowed as the alternative for each of the given building components that are listed here. In the next slide, we're going to go into a little more detail about the difference between the U factor versus R value, and also to the fact that these are assembly values versus just component values. So what is the difference between R values versus U factors, or U values as it's referred to also? So the R value is the inverse of the U value and vice versa. So in having numbers available for different components, 1 divided by the R value equals the U value, 1 divided by the U value equals the R value. So for example, if we have a component that has an R value of 20, its U value would be 0.05. Alternatively, an R value of R49 would have a U value of 0.02. So another important distinction when looking at this U factor alternative is that we are looking at the full assembly rather than the individual components of that assembly for value. So we're not just taking the value of the material that's in the framing cavity, we're looking at the full value of the assembly that cavity is located in. So we're taking into account the R value or U value of the framing of a wall and the percentage thereof as a component to the assembly of the full area of the wall. So we're looking at factoring in both the cavity value of the insulation material with the framing value of the framing component of the wall to get the full assembly value. And this applies to all components of the building, so walls, roofs, floors. So again, this is an alternative that's available to meet the prescriptive values that are listed in table R402.1.2.1. Usually it's going to be easier to just try to meet those component values rather than try to make these offsets. If you do have a building design that is really not fitting well with the prescriptive tables, then it may be worth looking at the ResCheck or HERS rating pathways as your compliance methods versus the prescriptive approach. So those previous slides covered the U factor alternative to prescriptive compliance. But there are a couple other notable alternatives or exceptions that are allowable under the base prescriptive packages. So two of those being installing R38 over 100% of a ceiling area shall be deemed to satisfy the R49 requirement, where you can get the full height and full R value of the R38 extending over the top plates of the exterior walls. So if you have an area where you have constricted ceiling height or attic height in the top of a building, the R38 for R49 exception is allowable, as well as the R49 for R60 equivalent value, as long as you're able to get that full R value over the full 100% area of the ceiling flat. So another alternative or exception that's available applies to cathedral or closed cavity ceilings. So R49 would be the minimum value for a cathedral or closed cavity ceiling, but there is an exception that would allow for a minimum of R30 in such assemblies, with similar guidelines of the insulation extending to full uncompressed height over the exterior wall plates and no compression throughout the full assembly. This reduction in value can be limited only to 500 square feet within a building, or 20% of the total insulated ceiling area, whichever is less. So next, we're going to get into section R402.2, which covers some of the specific insulation requirements and building assembly requirements for performance that are required in addition to the individual values, R values, U values requirements of section R402.1. So sections R402.2.1 through R402.2.15 are what we're going to be covering in the following slides. So these are the most relevant building systems and assemblies and the requirements for the prescriptive code. This list here in the slides ahead do not include all of the systems that are mentioned in R402.2, but again, a summary of the most common assembly types. So I suggest also looking through the full rule and the full rule of the Chapter 4, which will include other items that would not be covered during this training. So section R402.2.1 addresses unvented attic assemblies. So these would be cathedral or closed cavity roof assemblies. These are permitted as unvented assemblies under certain conditions. So the unvented space is completely contained within the building thermal envelope, meaning that there's no false spaces above or below. No interior vapor retarders, class 1 or 2, are installed on the ceiling side, so on the interior facing side of an unvented assembly. The next few slides will cover the different vapor retarder categories. Where wooden shakes or shingles are used as a roofing material, airspace is required above the structural sheathing and the roofing underlayment. And any air impermeable insulation, spray foam insulation, shall have a class 2 vapor retarder rating, and that's based on the density of the foam, or shall have a vapor retarder coating applied to the insulation after it's installed in direct contact with the insulation material. So there are different material assembly types allowable for unvented roof assemblies. There are 3 options available as listed here. Number 1 being air impermeable insulation only. So typically we're talking spray foam and spray foam installed directly to the underside of the roof deck. Second option being air permeable insulation only, which would mean that the full cavity is filled with air permeable insulation and rigid board insulation is added above the roof deck as a condensation control layer and to give continuous insulation value to that assembly. And then finally, a combination of air impermeable and air permeable insulation within the cavity. So this is also known as a flash and bat or foam and fill assembly, where spray foam insulation is installed directly to the underside of the roof deck. to an R value that is approximate to 50% of the total assembly value, and then the balance of the cavity be filled with the air permeable insulation. So the following are examples of the different assembly types that were described in the previous slide. These examples and some of the others that are contained in this training come from the 2020 Vermont RBES Handbook, and that is available. So I do suggest referencing that book for other drawings and details that identify some of the different building component requirements of the RBES code. So moving on to some of the other building components listed in Section R402. Eave baffles, so at the end of rafter cavities or rafter bays, baffles need to be installed that protect the insulation from airflow from the exterior, from the soffit of the insulation that's within the cavity. Attic access doors or crawl space attics do require access hatches that are insulated to an equivalent value of the surrounding surfaces. These access points also need to have a wood-framed or equivalent baffle to retain the insulation that's installed in the assembly surrounding it. These hatches also need to have some measure of weather stripping installed to create an airtight seam or gasket to the hatch when it is shut. And there is an exception for a more standard or traditional entry door to be used as an access point for an attic or crawl space. The next few items here cover exposed floors, basement walls, slab on grade floors, and crawl spaces. Key item to call out here on this slide is the definition of slab on grade floors. So any slab or floor surface less than 12 inches below grade shall be considered a slab on grade and be required to meet the slab insulation component values in table R402.1.2. So that would be R15 at the perimeter to a combination of 4 feet, or R10 perimeter plus R7.5 under the full slab. Crawl spaces are allowed and can be insulated as a basement would be, as an alternative to insulating the floor above the crawl space. It does stipulate, though, that crawl spaces shall be unvented in these circumstances. Crawl space wall insulation must be permanently fastened to the wall and extend down to at least the finished grade level, and then at least an additional 24 inches beyond that. Any dirt that remains within an unvented crawl space shall be covered with a continuous class 1 vapor retarder, with all joints of that vapor retarder sealed and incorporated into the foundation wall insulation. So the next few slides here get into some of the important considerations around the performance of the building as a system and issues or conditions to be aware of in managing condensation and moisture through building assemblies and within the building itself. So R402.215 calls out the requirements or the efforts to be made with above grade framed walls to protect those cavities of those wall assemblies from water vapor and condensation. There's different approaches that need to be taken in combination to provide the best protection against condensation from occurring within building assemblies. And these next few items here cover some of the building component items that can help manage that. So there are different vapor retarder requirements and different vapor retarder classes that will apply to different sections of the building. But as a general rule, class 1 or 2 vapor retarders should be installed on the interior side of all framed walls, with the exception of basement or concrete walls, foundation walls, below grade portions of any wall, and any construction where moisture or freezing will not damage the materials, which is going to be few and far between. The final item noted here on low permeability insulated sheathing basically addresses the attention to detail that needs to be taken when using continuous insulation on the exterior side of a framed wall. In doing so, Class 1 vapor retarders should not be used. If one will be used, it does require that it is an engineer-approved design. For any assembly with a continuous insulation used on the exterior of that wall, Class 2 vapor retarder or greater shall be used for these assemblies, and we will go into more detail on that in the coming slides. So Class 3 vapor retarders, which are pretty much vapor open materials, are allowable on the interior side of frame walls should any of the conditions that are listed here below can be met. So any vented siding or cladding over the following sheathing types: fiberboard, gypsum, plywood, CDX, OSB, or solid wood sheathing. So basically this means as long as you have a rain screen type assembly for your exterior cladding, a Class 3 vapor retarder can be used. It's also allowable on walls that have continuous insulation on the exterior, given that those values meet a minimum of R7.5 in the continuous insulation over a 2x4 wall, or R11.25 on a 2x6 wall. So building air tightness and getting very good separation of airflow from the interior of the building into exterior assemblies such as wall and roof assemblies is the primary strategy for preventing moisture migration into building assemblies. But given those efforts, ultimately there will be a mechanism of transport for moisture vapor into building assemblies. And this is where the use of the different vapor retarder classes come into play. So this chart here gives you an overview of the different vapor retarder classes, what the permeability ratings are of those different materials, how they're described, and some of the examples of these materials that can be put together into a full building assembly. So choice of components and materials into wall and roof assemblies especially are critical to the overall performance and long-term durability of these assemblies. So these next couple slides here come from the RBES Handbook and show some different wall assembly types that are compliant with the RBES code prescriptively. So these detail some of the continuous insulation assembly options as well as cavity fill only. And some of these building assembly types continued. So these two wall assembly types shown here are not the only risky wall assemblies out there, but probably a couple of the most common. The examples being shown here are at the top, a continuous exterior insulation of an R value that's probably a little too low for the thickness of the cavity itself. So R5 continuous over a 2x6 wall cavity. That type of assembly can create the conditions for condensation to occur on the sheathing behind the foam. And in this assembly also a Class 1 vapor barrier, a poly vapor barrier, is used on the interior behind the drywall. This is a vapor barrier sandwich assembly, so you have very limited, if any, drying potential in either direction with this type of assembly. And similarly in the assembly listed below that, which is a nail-based panel where your sheathing is on the exterior of the foam. Similar considerations here where you have a poly vapor barrier on the interior, the vapor permeability of the foam itself on the exterior is low. So again, this is another assembly type where you may find high levels of moisture accumulating in the wall with minimal potential for drying. So these are a couple assembly types that should be avoided if at all possible. And referencing back to some of the alternative options with the different vapor retarder classes and vented rain screen cladding assemblies to allow for maximum drying potential for wall assemblies. Section R4023 covers fenestrations or windows and building glazing. These items here summarize the content of Section R4023, but basically give examples of alternatives and exemptions and other pathways to the fenestration requirements in Table R402121. So an ongoing area of importance in building performance with the RBES code are the requirements for building air leakage. In general, residential construction and construction in general is creating much tighter building assemblies than we have seen than in previous generations. And ultimately, this is a direction we want to be going in, and protects the building envelope to a great extent from moisture damage by the unmitigated flow of air through building assemblies. So Section R4024 covers the details and the mandatory air leakage pathways that need to be addressed within the building envelope, and the criteria for these assemblies and the materials to be used in creating a durable and continuous air barrier. So Table R402411 details requirements for the alignment of the building air barrier with the insulation measures. So this is an important factor for performance within the building, that the air barrier as a building assembly is aligned and appropriately connected with the insulation assembly of the building. Generally speaking, insulation materials cannot be used as an air barrier. An exception for this is spray foam, which under the right conditions and the right assembly types, and when installed to minimum thicknesses, can provide an air barrier as well as an insulation barrier at the same time. But the key here being that the air barrier is a continuous, durable layer and part of the building assembly that has been put together in a way that any joints or disconnects that could potentially exist in that assembly have been addressed with appropriate materials to make it continuous. So these next two slides here cover some of the highlights of the different assemblies called out in Table R402411 to be aware of. So floor cavity, framing insulation, exposed earth and unvented crawl spaces, as we mentioned before, requiring a vapor retarder or vapor barrier. Another important distinction is that air sealing shall be provided between garages and conditioned spaces, so making sure that there is a good air disconnect between garages from the adjacent living space. Other notable requirements from Table R402411 requires the use of insulation contact and airtight rated ceiling light fixtures, as well as other electrical or fixtures that will penetrate the building thermal envelope. Exterior walls adjacent to showers and tubs need to have a rigid air barrier separating the exterior wall from the shower and the tub, and have insulation in that cavity. Basically, this means you can't put a shower surround against an open wall cavity that just has fiberglass or other air permeable insulation in the cavity without some sort of durable air barrier over that cavity fill insulation. Air barriers should be installed in common walls between dwelling units and multifamily settings. So these are just, again, some of the highlights of the different components called out in Table R402411, and I suggest that you look through the full table requirements in the full code. So the next couple slides here go into some detail about building assemblies and how they relate to the air barrier requirements and alignment with insulation. These examples again come from the RBES Handbook. This image here coming from the handbook calls out some of the critical details that are defined in the handbook and come from Section R402411. So I suggest taking a look through the handbook also to see what these corresponding details show. So building air leakage testing is a new requirement of the 2020 RBES. So moving forward with the Vermont Code, any new construction or addition will be required to be tested upon completion for its total air leakage rate. And the buildings per RBES shall not exceed 3 air changes per hour at 50 pascals or 3 ACH 50. Testing needs to be conducted in accordance with the specifications called out in this section and need to be performed by a qualified individual, as noted in this section also. A written report of the results shall be signed by the person conducting the testing and shall accompany the code certificate upon completion. Section 402.42 specifically calls out requirements for fireplaces and wood burning appliances in new construction. Referring back to Section 305, which covers combustion safety, any building built to meet the Vermont RBES standard is considered an unusually airtight building assembly, so there are specific combustion requirements that fall into play as a result of this. So essentially this means for wood burning fireplaces that airtight gasketed doors are required as well as combustion air. Full detail on these requirements and the other requirements of combustion safety can be found in Section 305 and the subsections listed below. So again, to just reinforce what was mentioned in the previous slide from Section R305 regarding combustion safety, basically any fuel burning appliance in a building needs to be either direct vented or closed combustion and have outdoor combustion air provided directly to the appliance. So basically any combustion air cannot be provided from within the building. So further detail, as mentioned, is provided in the full section R305. So section R403 of chapter 4 covers building systems, so primarily the mechanical systems installed in residential buildings. We're not going to go into detail of these different components of the building, but these are obviously elemental components of any residential building and things that a builder should be aware of to be able to make their mechanical contractor aware of the requirements and to follow the guidelines stipulated in the RBES code that pertain to mechanical equipment. Similarly, for electrical systems, section R404, R4041 pretty simply states that 90% of the lighting in the building shall be high efficacy lamps. Basically, we're talking LED fixtures or equivalents. Another distinction called out in section R404 is in regard to electric resistance heating equipment. So building heating with electric resistance is prohibited with a few significant circumstances allowing it to some extent. Heat pumps having supplementary electric heat resistance heat shall be certified cold climate heat pumps only and have controls that prevent that supplementary electric heat operating when the heat pump can meet the full heating load of the building. The exceptions for the use of electric resistance heating comes into play with the replacement of existing electric resistant units. So if you have an existing building with failing electric resistance heat, those can be replaced with new electric resistance units. There is an allowance where limited spaces where other heating sources are cost prohibitive or impractical. Electric resistance can be used in spaces such as bathrooms, stairwells. So this accounts for adoption of whole house efficient heat pump systems and giving some allowance for allowing the distribution limitations of some of those systems to allow for electric resistance heat. Buildings with cold climate heat pumps as the primary heating system. Supplemental electric resistance can be used in the circumstances listed above, the limited areas as noted above. Where that electric resistance is controlled to prevent it from operating at an outside air temperature of 5 degrees or higher, basically meaning that the heat pump can meet the full load of the house as mentioned in the previous slide. And to allow for this exception, the building must have a building air tightness tested at less than or equal to 2 ACH 50. And finally, the final exception for electric resistance heat is in multifamily buildings with heating loads less than or equal to 6 BTUs per hour per square foot at design temperature. Another new addition to the 2020 RBES code is requirements for electrical vehicle charging, which come into play for multifamily developments of 10 units or more, as required in Table R404.3. Single-family residential projects that are required to meet stretch code need to have at least one level 1 electric vehicle parking space with an accessible socket. The final section that we're going to discuss today is the mechanical ventilation requirements for the 2020 RBES. So this covers Section R304. This is the design criteria for residential ventilation systems. Mechanical ventilation is an important component of any new construction, given that we're getting much tighter building envelopes and we need to manage indoor relative humidity as well as indoor pollutants. So being aware of the requirements of the ventilation systems for new construction is definitely a key component for successful outcomes. So whole house ventilation is a mandatory requirement of the RBES code. So every home or building built to the RBES standard shall be mechanically ventilated by a whole house ventilation system as defined in Chapter 2. That was the section on the definitions I referred to at the beginning of the training. The option exists for that whole house ventilation system to be either exhaust only or balanced, balanced meaning heat recovery. Compliance can be met for the ventilation requirement in Section 304 prescriptively by meeting the minimum requirements for fans in Table R3046, as well as a performance requirement being an option. Table R304.6 is the prescriptive fan capacity requirement if you're going to meet the mechanical ventilation requirement prescriptively, meaning that given the number of bedrooms listed in this table here, installing a fan of the appropriate design and flow at the minimum rated capacity listed here and the minimum number of fans will qualify you as meeting the mechanical ventilation requirement for RBES prescriptively. It is worth noting, though, that meeting the code prescriptively for this requirement may not be the best performance pathway to serve the whole house and manage indoor relative humidity and building indoor air quality. Local ventilation requirements, sections R304.2. So bathrooms containing a tub, shower, spa, or similar fixture and not included in the whole house ventilation system need to meet the capacities required in Table R304.2. Whole house ventilation systems that are serving both this local requirement and the whole house ventilation requirement shall be sized to meet the capacity rates that are required in Section 304.6 and meet the other requirements listed in Section 304.3 that apply. Table 304.2 covers those minimum local ventilation requirements for bathrooms. So if it's a standalone bath fan with no whole house ventilation into the space, the fan needs to have a minimum capacity of 50 CFM. Or if the local ventilation requirement is going to be met as a part of the whole house ventilation system running continuously, then the net flow at that port shall be a minimum of 20 CFM. So as an alternative for meeting the prescriptive approach for mechanical ventilation of Section R304, there is the performance option for ventilation, which requires some calculations to be done to give a full house ventilation rate and runtime, and it takes into account the square footage of the house, the number of occupants, and building exposure, as well as air leakage rates. The allowable standards to be used for the performance option are the ASHRAE standard 62.2/2016, the Building Science Corp standard 01-2015, and the passive house ventilation options or requirements. Ventilation controls basically stipulate that the systems need to be set to be run remotely for continuous operation, or be provided with an automatic control for intermittent use. Any whole house ventilation controls shall be accessible, readily accessible. Basically, the mechanical ventilation system needs to have some sort of control mechanism in place that allows it to run independently of user input. So it needs to be able to be run throughout the day on its own, with options for changing the operational speed depending on the system designed installed. Finally, in regard to mechanical ventilation system requirements, basically just stipulates that the equipment should be installed according to the manufacturer's instructions and in accordance with the guidelines set out through sections R30491 and R30498. And the final two mechanical requirements of note that are required: clothes dryers need to be vented directly to the exterior of the building. They cannot be exhausted into other places, such as garages or crawl spaces. Range hoods, exhaust hoods that are capable of moving air in excess of 400 cubic feet per minute need to have a makeup air system installed that provides an equivalent amount of airflow equal to the exhaust rate. These makeup air systems need to be equipped with a way of closing or closure and be automatically controlled to turn on and off simultaneously with the use of the exhaust system. So that completes the overview of the prescriptive compliance with the 2020 Vermont Residential Building Energy Standard. The content that was provided in this session covers, again, the prescriptive pathway for compliance with the RBES code. There are the other alternatives of the ResCheck software and the HERS rating compliance pathways. More information can be found on these methods in the full code book, as well as in the RBES Handbook. This session was a pretty comprehensive overview of the key components that a builder or general contractor or designer would be required to know and to follow to be compliant with the RBES code, but again does not cover the full detail and the full rule of the law. So the full code should be referenced in order to adhere completely to the requirements of the code. But understanding the general requirements that were provided in this session should take you pretty much all the way you need to be able to meet and understand the requirements of the 2020 Vermont Code. So thank you for your time. Again, more resources are available through the Energy Code Assistance Center and the Vermont Department of Public Service. Also feel free to reach out to me directly with any questions that you may have. Thank you.